Okay, so base de frenet. Okay, base de frenet. It uses tau, normal, and the vector b. Okay, so the tau vector is given by v divided by its magnitude. Okay, so if we have a trajectory and the point M, we say that the velocity of the point M is always tangent to the trajectory that it makes. Okay, so here we're going to define now a tangential unit vector which we call tau in the direction of vitesse. Then by definition we define a unit vector to be the vector divided by its magnitude. Okay, then another expression of tau which is well proved, but we're not going to do that here because it's a lot of work and you're not going to be tasked to prove that tau is given by two definitions. It's also given by dom over dt or ds, sorry. Okay, where s is just the axis keveling, that is the path. Okay, when you, it's like you name this path, the length of this path to be s. Okay, but don't worry about the details. So now, from these two, formulas of tau, I can deduce what vector vitesse is. So our vector vitesse will be equal to the magnitude of v, then in the direction of tau. Okay, as simple as that for the first one. Now for the second one, I'm going to use the general definition of v. The general definition of v is dom over dt. Okay, we all agree with this is the general definition of v. Now, from this general definition of v, I'm going to make tau appear in this equation. That is, I'm going to divide by ds, because once I do this, once I do this, I'm going to have tau. Okay, but this is not my equation, so I have to make sure that I also multiply by ds then over dt. So that this is what I say completing the chain rule. Okay, so when you divide this and this, you're going to have dom over dt, which is from the general equation. But the reason why we did this, boys, the reason why we're doing this is we're using the second definition to find the vector vitesse. Don't worry about, don't forget the objective of doing this. Okay, so from here we'll discover that our vector vitesse is also given by ds over dt. Then this is none other than tau. Okay, now boys, we have two definitions. From these two, we have two definitions of v. Okay, the first definition of v is this, and this is the second definition of v. So which v is equal to v, isn't it? The vector vitesse is equal to vector vitesse. What does this imply? This implies that ds over dt, the second definition of vector vitesse, is equal to the magnitude of v, the first definition of vector vitesse. What can you say from this equation? From this equation, we can deduce that on P de BK, the vector vitesse is equal to ds over dt. As simple as that. So the magnitude of the vector vitesse is also ds over dt. So what is the essence of this information? So sometimes they might give you the equation of the axis keveling. Maybe it will be as a function of time. So when you just differentiate this with respect to time, it's the same as finding the magnitude of v, because this is equal to ds over dt. Okay, or if they tell you to find ds over dt, you just find, sometimes you might be given a vector v, then you just find its magnitude, then that's ds over dt, or depending on what I've given you. So from the base de frenet, we have three vectors. We've only defined one vector which we said is tau is given by the vector divided by its magnitude, vector vitesse, or also defined to be dom over ds. Okay, actually from this discovery, from ds over dt is equals to the magnitude of a vector, we can actually show that tau is also dom over ds. It's very simple. From the first definition, how do you define v? Okay, v is defined to be dom over dt, right? Then how do you define the vector vitesse now, the magnitude? We now define it to be ds over dt. Okay, then from here we can cancel out this and this. What are we going to have? The OM over the D over the S, I mean. So if you can't remember this definition of tau, at least remember this definition of tau, and also remember that the magnitude of a vector can also be the derivative of this abscissa curvature over with respect to time. Okay, so this definition is very important. Okay, now we've only defined one vector, which is tau. Let us also define the normal vector. The normal vector is given by the radius r, or some books will use rho. Okay, rho. Okay, this is the radius. Then the tau over ds. So once again, we're not going deep into proving these formulas, but they are well proved. Okay, so from now on, what we're doing in this course is knowing how to apply these formulas. So you need to master the formula for the normal vector. Okay, now you will see why it's important. Now from what we have now, we can now calculate the vector vitesse. So we said the vector vitesse was given by the magnitude of v tau. As simple as that from the definition of tau, right? V over the magnitude v. Or in other words, if in other words, the other way you can do it is you define vector vitesse of the point M in general, which is dom over dt. Okay, then here you make dom over ds appear, then you get rid of ds, of course, so that you have tau. Then we said ds over dt is what? Okay, ds over dt, this was none other than the magnitude of v. Okay, so here we're going to have, and this is tau. Okay, so we're going to have tau. So this is going to be the magnitude of v over tau. Or if you want, you can represent the magnitude of v to be just a smaller v without anything because it's magnitude. So v tau. Okay, so these are two ways you can give me the vector vitesse. Either you just go directement from the definition of tau, or you use the general definition, but this one requires that you remember another definition of tau, which is dom over ds. C'est bon? Okay, so another interesting thing that we're going to define is vector acceleration. So if we have a trajectoire comme ça, n'est-ce pas, and the point M here, we know that what's the direction of the vector vitesse? Tangent, okay, tangent to the point M, right? Now, for the vector acceleration, we won't just be tangent, we'll have two components, one which is tangent, the other one which is towards the center of a circle of radius rho, okay, which is the normal vector. So one will be, so we'll have two components. So acceleration will have two components. Okay, we'll have one component which is the tangential acceleration, then the other component which is the normal acceleration, that is perpendicular to the point. C'est bon? Okay, so now how are we going to show this, that there are two components? How are we going to show? Let's show that there are two components of acceleration. Okay, so from the definition of vector vitesse, we said vector vitesse is equals to v tau. Okay, where v is none other than the magnitude of v. Okay, now acceleration will be given by, the general definition of acceleration is what? The derivative of v with respect to time, isn't it? Now the derivative of v with respect to time is none other than, so here our expression of v is v tau. Okay, then with respect to time. Okay, so here we're going to apply the product rule. Okay, we have two things, so we're going to derivate dv over dt, keeping tau constant, then plus the second component will be, we'll keep v constant, we're going to be d tau over dt. Okay, now the first component, it's in the as a function of tau, but then this one is as a function of d tau over dt. So you deal with this expression. Okay, this is why it was important. So one to this one, yeah, the first component is tangential, the second component is normal. So we said that from the three vectors, okay, there's the normal vector, and this normal vector, for now I will go with that you memorize. It's rho d over ds. Okay, so we're going to make this expression appear in our expression of acceleration. So getting this part of the expression d over dt, let us now, so this we can write it as d, okay, over ds. Then to complete it, I'm going to say ds over dt. Okay, I haven't changed anything. Okay, I've divided and multiplied. Okay, now d over ds. Here, from the expression of the normal vector, we have d over ds. It's not complete. Yeah, so from the expression of the normal vector, we have d over ds. This is why ds was appeared in my expression of d over dt. So I know that d over ds is not, it, d over ds is what? Is the normal vector divided by the radius, rho. Okay? Here we just make d over ds as the formula. Here we're going to have the normal vector divided by rho. So here I'm going to replace it by, so I'm going to have ds over dt, then rho and the normal vector. Okay? Yeah. Now, what did we say ds over dt is? We said that ds over dt is none other than the vector what? The magnitude of the vector vitesse, if you remember, which is just represented by v. Okay? So here we're going to put, so our expression is going to be rho v n. Okay? Now, this part of the expression was just this part. So here you're going to replace it by v rho n. Okay, so the complete now acceleration, okay, the complete acceleration vector will be, dv over dt tangent plus, if I multiply those terms, I'll have v squared over rho, the normal vector. So, boys, these are what we call the two components of acceleration. We have the tangential acceleration, which is represented by t, which is dv over dt, to tangential because the first one is in the direction, is in tangent to the point m, is in the direction of the tangent. Then the second one is in the direction, is normal. Okay, y gamma n, which is v squared over rho n. So that's how you find the two components of acceleration.